anytime we're working with a limit problem, the first thing that I'm going to try with the limit problem is to plug the number in. And if I plug the number in, well, let's see, if I plug in 3 to the denominator, we definitely get 0. And if I plug in 3 to the numerator, 3 squared is 9, minus 15, I think should be at -6, plus a 6. So we also got 0 over 0, which means go do some algebra. And the algebra that we're going to need to do here is to factor. I take that limit as x approaches 3, thinking about the numerator. Now, this is a tip that I didn't say the other day, but if we know that plugging in 3 gives us a 0, then I already know that one of the factors is x minus 3. And if you're ever having trouble seeing how something is going to factor out, just know that that's a nice tip that you can use. Since I know that one of the factors is x minus 3, we kind of don't have a choice on what the other factor is. Because if I look at that 6, I need something times -3 to give me 6. That's going to need to be -2. And on the bottom, I've got 3 minus x. Okay. That x minus 3 over 3 minus x almost cancels out to give us a 1, but not quite. This is something that shows up so often in limit problems, when we're doing some other things down the road in Math 16A, that I want to take a moment to talk about how that x minus 3 over 3 minus x is going to simplify. And there are a couple of ways to think about this. If I have x minus 3 over 3 minus x, one option is to think about that denominator and factoring out a negative number. So in the denominator, if I were to factor out a -1, or really I'm kind of just factoring out a negative, then what I would have to multiply by to get back to that 3 minus x would look like I'd need a -3 so that when I distribute that negative in, it becomes positive again, and I'd need a positive x so that when I distribute the negative in, I get that negative x back. So it turns out that x minus 3 over 3 minus x actually simplifies to be -1, not +1. And here we can see that the x minus 3 over x minus 3 is going to give us -1 also. So you can factor it out, or we can just remember that if I have something that looks like x minus 2 over 2 minus x, this is always going to simplify to be -1, except when x equals 2. So for any value, that got really messy, but except when x equals 2. And if x equals 2, then we already have a problem because we'd have a 0 in the denominator. So anyway, we'll worry about that later. In this case, in terms of that limit, that x minus 3 over 3 minus x, in the limit, that's going to go to a -1. So this is equivalent to the limit as x approaches 3 of -x minus 2. So our answer here, now that we're ready to plug in that 3, is actually going to be -1. And from a previous life, at some point in time in pre-calculus, you probably practice graphing rational functions. This rational function has a vertical asymptote at 3, and it has a horizontal asymptote at y equals 2. And this function looks like this. And we'll spend more time thinking about how to graph functions in 16A, but for now, just take my word for it. This graph should look like this. The particular limit questions that we might concern ourselves with here then are thinking about the limit as x approaches positive infinity for that function, the limit as x approaches negative infinity for our function here. And these two together, they're asking us what's happening way out on the edges of the graph. And that way out on the edges of the graph idea is the horizontal asymptote. So anytime that we're asked to find a horizontal asymptote, that question is secretly asking us to evaluate each of these limits. Now, if I have a picture, then I can evaluate those limits. We'll do it with algebra in just a second. But using the picture, I can see that on both edges of the graph, as my y value is as my x value is approaching negative infinity, my y value is getting close to 2. And the answer to a limit problem is always what the y value is getting closer to. I drew that on the negative infinity side. If I go to the positive infinity side, as my x gets larger and larger and larger, my y values are getting closer to 2. So we say that that horizontal asymptote is at y equals 2. There are two other interesting limits on this graph, or at least two other interesting limits on this graph, and that's to look at what's happening when x approaches 3. So graphically, if I were to ask for the limit as x approaches 3 from the right, and remember that plus says we go to an x value of 3 and then we add a little bit. So if I go to an x value of 3 and then I add a little bit and hop on the graph, where is the graph taking me in terms of a y value? And the graph is taking me towards positive infinity. If I asked for the limit as x approaches 3 from the left of our function, so I go to x equals 3, but I subtract a little bit, and then I think about where I am on the graph, and then I inch back closer to 3, this is taking me to a y value of negative infinity. So if we were given the graph for every function, or even if we knew how to graph each function, then talking about these limits, one option is to think about them graphically. By the way, this guy was a horizontal asymptote when we're taking that limit as x approaches positive or negative infinity. And this is a vertical asymptote when my answer to the limit is a positive or negative infinity. So this is my vertical asymptote. Now I want to go back because the reality is that most students don't look at this and immediately know what the graph looks like. And we're also expected to be able to show how we get answers to these limits using some algebra skills. So we're going to go through and do both of these, well, all 4 of these questions using our algebra skills. There are a couple of things that we have to establish first. So I don't know the answer to this, but one of the cool things is we're all sitting in front of computers. So let's see if someone can figure it out. Does someone know who the richest person in the world is? If you know, type it in the chat. Maybe you can Google it. I don't know.
Bezos or something?
Bezos, okay. So from my perspective, Jeff Bezos is rich. Yeah? Okay. So let's go with Jeff Bezos. I don't know if that's true, but so as far as I'm concerned, Jeff Bezos might as well have an infinite amount of money relative to how much money I have. So let's say that Jeff Bezos has that infinite amount of money. Does he have any kids? No idea. Okay, so we won't worry about that. Let's say he's feeling very philanthropic and he is going to donate all of his money to 3 organizations. So he's got from my perspective, an infinite amount of money, and he divides it evenly among 3 of his favorite organizations. Everybody still has a whole heck of a lot of money. So infinity divided by a number, it actually doesn't matter how big this number is. Infinity divided by a number is still heading towards infinity. Now, on the flip side, let's say that I have, let's say that I had $10, and I was like, you know what? I'm going to share those $10 with everybody at UC Davis. Well, if I decide to share those $10 with everybody at UC Davis, that's students, staff, faculty, what's that, like 100,000 people? Something crazy like that? It may not be 100, I'm probably exaggerating. 60,000 people between staff, students, and faculty. That is really almost nothing. It's a very small number, really small. Sorry guys, I don't have all the money. But in this limit, if I have 10 divided by a really huge number, this is going to 0. So two of the most important limits that we're going to encounter, and if I generalize this in terms of kind of what can happen with a limit, if I end up, we already know that if I end up with 0 over 0, this is do some algebra. If I end up with infinity divided by a number, well, that's just infinity. And if I end up with a number divided by infinity, that's headed to 0. I've got one more limit that I want to think about conceptually, and then we'll be ready to attack finding the asymptotes for this problem. So the other important limit that we need to figure out is what happens when we have a number divided by 0. Somebody pick a number, type a number into the chat, anything you want. Great, 7. That was weird. 3 people typed 7 like at exactly the same time. Okay, popular number, noted. So if I have 7 and I divide it by 0, we all know from back in the day, teachers said, wait, you can't divide by 0. Well, we're not really going to divide by 0 because we're thinking about limits. So we're getting really, really close to a number. We're not actually going to get to 0. So let's say I just got kind of close to 0, like 0.01. Well, if I wanted to know what this was equal to, that 0.01, the other way that we can write that is as a fraction. So this would look like 7 divided by 1 over 100. And then dividing by a fraction is the same as multiplying by its reciprocal. So 7 divided by 0.01 leads us to 700. Since we're taking this limit and we're getting closer and closer and closer and closer to 0, if I just add a couple more zeros in there, or shove a couple more zeros in there, if I added 0, it wouldn't do anything. But if I shove a couple more zeros in there, 1, 2, now that means that I've got a couple more zeros down there and a couple more zeros out here. So as the denominator gets really close to 0, what's happening to the limit is that number divided by 0 is getting really big. Just put this back into red. It's getting really big. Now there's a subtlety here, because when we're talking about 0, I could be approaching from either the right-hand side of 0, meaning thinking about positive numbers, or the left-hand side of 0. So what we say is that a number divided by 0 is either headed to positive infinity or negative infinity. And if we have to graph it, then it's our job to figure out which one. And as has been pointed out, it is true that none of these values are defined, but that doesn't mean that the limit isn't defined and that we're not going to talk about the limit. right? If you got a number over 0 and just wrote DNE or does not exist, that's not getting you full credit in a calculus sense. We still need to understand what's the behavior of our graph or our function. Okay, now that we've got this, we're going to go back and attack our actual function and find those vertical and horizontal asymptotes. Let's start with horizontal asymptotes first. So that question of finding the horizontal asymptote says that we're going to be taking the limit as x approaches, and technically we want to check positive and negative infinity. So I'm going to start with positive infinity here. And I've got 2x over x minus 3. The first thing we're going to try with any limit problem is to plug it in. Now I know infinity is not a number. We can't plug infinity in, but we still kind of can. So if I plug infinity in, 2 times infinity is, well, it's infinite. And infinity minus 3 is, that's right, also infinite. Which means, kind of like 0 over 0, infinity over infinity is also going to tell me, go do some algebra. The algebra that we're going to do when we have infinity over infinity for this limit is to find the largest power of x in the denominator and divide every term by it. Alternately, we can find the largest power of x in the denominator and factor it out of every term. Those two mathematically are going to work out to be equivalent. I think it's a little bit easier to see if we divide every term by the largest power of x. So here, when I look in the denominator, we really only have one power of x, that's x. So I'm going to divide every term by x. Now a couple of these simplify because 2x over x, the x over x part is going to 1, and that over x part is going to 1. So that when we take this limit, in the numerator, I have 2, and in the denominator, I end up with 1 minus. Remember, if I plug in that infinity here, if I had $3 and I tried to share it with everybody, no one gets any money. Or rather, everyone gets no money. So the answer to this limit is 2. Now, I said when we're talking about horizontal asymptotes, we really want to check from both the positive and negative side. But in this case, nothing would have changed about the math that we did. So we can actually write this as plus or minus infinity on both of these. And none of the values are going to change. Because even if I put in a negative infinity here, the only thing that would happen, oh, you know what, I probably should write it out. I was trying to be lazy, but it's going to change that sign. So I shouldn't be lazy. I should write this out. So the limit as x approaches negative infinity, we would be doing exactly the same math here. But what would change is in the denominator, because that x is headed to negative infinity, this would actually look like 1 plus a 0. We still get the 2. We'll just be careful about the notation there. So now I know that our horizontal asymptote is, and since the answer to a limit is what y is trying to be, the value for my, the equation for my horizontal asymptote is y equals 2. I'm going to pause there just for a second, and then we'll talk about finding the vertical asymptote. And we'll do more practice with this, don't worry. Still early. And someone was an awesome timekeeper for me the other day and cut us off. So if someone can be my timekeeper again today, and at about 11:20, remind me if I haven't stopped us, and we'll take a short break. Okay, can I explain again what we plugged in for X? Yes. So at this step, I'm plugging in the infinity for X. So I've got in my numerator, X over X, they canceled out, they became 1, so I really just have a 2, there's nowhere to plug that in. Here, X over X is 1, so there's nowhere to plug that in. But this 0 came from looking at 3 divided by positive infinity. And 3 over infinity in the limit is headed to 0. Doesn't mean 3 divided by infinity is equal to 0, but in the limit, as X approaches infinity, 3 over X goes to 0. I don't know if that helps. I'm guessing if we do more problems, it'll help. Okay. Let's go ahead and talk about those vertical asymptotes, and then we'll get a couple more examples for your notes in terms of both horizontal and verticals. So change that to say vertical. The first thing that we should address in terms of vertical asymptotes is those are happening when my y value is approaching either positive infinity or negative infinity. So that means vertical asymptotes are happening when we have a situation where I've got a number divided by 0, or when we're talking about logs later, but those are coming up in 16b. For now, when we're talking vertical asymptotes, I'm looking for X values that would give me a number divided by 0. So thinking about our function, 3 is a value of X that would make us divide by 0. So if I want to find those vertical asymptotes, I have to do the calculus-y thing and look at the limit as X approaches 3 of 2X over X minus 3. And in particular, I'm going to look at that limit as X approaches 3 from the right and from the left. So let's start by looking at the limit as X approaches 3 from the right. The first thing we're going to do with any limit problem is to plug the number in. Well, if I plug in 3, then in the numerator I get 6. And in the denominator, when I plug in 3, I get 0. Well, 6 over 0, I already know is headed to either positive infinity or negative infinity because I got a number over 0. I'm going to use the notation that Dr. Kuba usually uses, which is now that I have a number over 0, I need to know, was that 0 a little bit positive or a little bit negative? Well, this says that I took 3 and I added a little bit to it. So if I have a number in here for X that's 3 plus a little bit, then when I subtract the 3 back off, I've got a positive number, which means 6 over a slightly positive 0 is headed to positive infinity. If I come back through and I look at the limit as X approaches 3 from the left, we're going to start off exactly the same way. I'm going to plug in the number. So in the numerator, I get 6, and in the denominator, I get 0. Then I'm going to come back over here and ask myself, well, if I was at 3, but I subtracted a little bit, and then I subtracted 3 more, I'm going to be a little bit negative. And 6 divided by almost 0, but a little bit negative, is headed to negative infinity. So I'm going to say that the equation for my vertical asymptote is the X value that we were approaching when the Y value became infinity. So the equation for our vertical asymptote is x equals 3. The first thing we're going to try with any limit problem is to think about plugging in the number. I know infinity is not a number, but we're still going to plug it in. So if I think about plugging in infinity, infinity squared, still infinite, multiply that by 3, still infinite, add 2 to that, still infinite. Infinity minus 2, still infinite. Infinity over infinity, I know someone said L'Hopital's last time, we're going to have to wait a little bit till we can use that. For now, infinity over infinity, just like 0 over 0, says go do some algebra. And the algebra that we're going to want to do here is to find the largest power of x in the denominator and to divide every term by that. So my largest power of x in the denominator is x. And I'm going to divide each term by x. So I've got 3x squared over x plus 2 over x over x, and minus 2 over x. Now I'm going to simplify all the terms that I can, meaning x over x, this is headed to 1, and x squared over x is going to simplify to just leave me with x. So this is the same as the limit as x approaches infinity of 3x plus 2 over x over 1 minus 2 over x. We've manipulated the problem a little bit, so we're going to plug in that infinity again and see if we have some resolution. So if I plug in the infinity in the numerator, 3 times infinity, well, that's still infinity. But 2 divided by infinity, that's headed to 0. And this 2 over infinity is also headed to 0, which means we have an answer for our limit. We are going to positive infinity here. Yay! I was pausing for a second, not seeing a ton of questions, so I'm going to keep rolling. Let's say that I've got the limit as x approaches infinity of, oh, I was like writing the same problem again. Let's say I've got 5x cubed plus 2x squared minus 1 all over 3x to the 4th plus 7x. Sure, why not? Got a question in here. Why did we not do the minus infinity like for the first question? Okay. If I were trying to find horizontal asymptotes, that phrase, find the horizontal asymptotes, means that we need to look at both the positive infinity side and the negative infinity side. But we might also just be asked to evaluate a limit, right? So maybe I should have put instructions up here, but if we were just asked to evaluate the limit, then that question doesn't say go do extra things. We're just going to answer specifically the question that they asked us. So the limit as x approaches infinity. Yeah. Same thing here. I'm only going to concern myself with x approaching positive infinity for the moment. Okay. Now that we're looking at x approaches positive infinity, first thing we try with any limit problem is to plug it in. Well, if I plug in that infinity cubed plus some more infinity minus a 1, top is headed to infinity. Infinity to the 4th times 3 plus some more infinity, also headed to infinity. Do some algebra. So if we come in here to do some algebra, I am going to look for that largest power of x in the denominator, which is going to be x to the 4th, and divide every term by that x to the 4th. So I'll have 5x cubed over x to the fourth plus 2x squared over x to the fourth minus 1 over x to the fourth, 3x to the fourth over x to the fourth plus 7x over x to the fourth. And then just like on the previous problem, I'm going to simplify each of those terms as much as I can. So that limit is going to be equivalent to the limit as x approaches infinity. 5x cubed over x to the fourth, I'm going to be left with 1x in my denominator. So 5 over x. Here, 2 of the x's are going to cancel out, so I'll be left with 2 over x squared and a 1 over x to the fourth. In the denominator, the x to the fourth over x to the fourth, I've got a 3, and one of those x's will cancel out, so I've got 7 over x cubed. Well, when I walk in here to take that limit, now that it's simplified as much as we can, when I plug in infinity, I got a whole bunch of zeros. 5 to the x is headed to 0. 2 over infinity squared, that's headed to 0. 1 over infinity to the fourth, that's headed to 0. I've got a 3 in the denominator. And 7 over infinity cubed, that is also headed to 0. So it kind of got squished in here. But I ended up with 0 divided by 3. And I didn't put that on my list of possible answers, like 0 divided by a number. But 0 divided by a number is 0. So my final answer for this limit here is 0. First thing we're going to try with the limit problem is to plug it in. When we put the infinity in, we get infinity over infinity. It's telling me to go do some algebra. So I'm going to look for the largest power of x in my denominator. So that's going to be this x squared term. And I'm going to take that limit as x approaches infinity, dividing each term by x squared. I'm going to simplify each of those terms. So 7x squared over x squared, end up with a 7. 3x over x squared, one of those x's cancels, and I've got 3 over x. X over x squared, one of those x's cancels, and I've got 1 over x. And 2x squared over x squared, I end up with a 2. When we evaluate this limit, when I put in infinity now, 3 divided by infinity is going to 0, and 1 divided by infinity is also going to 0. And this whole thing is going to simplify to be 7 over 2. Now, if we take those 3 examples that we just did, I know 3 examples is not like giving us a proof here, but we have 3 different outcomes for those examples. In the first one, when we took the limit as x approaches infinity, we got infinity. In the second problem, we took the limit as x approaches infinity and got 0. And here, oh yeah, thanks for pointing out my negative. -2. Negative. Thank you. -7/2. Okay. Fast forward back to what I was saying. First example, we took the limit as x approaches infinity, we got infinity. Second example, we took the limit as x approaches infinity and got 0. This example, we took the limit as x approaches infinity and got a number that isn't 0. Those are really kind of our 3 possibilities of what's going to happen when we have one of these rational functions and we're taking that limit as x approaches infinity. So we can summarize what's happening in each of these based on those largest powers of x. So here, my largest power of x in the numerator and denominator matched up. So that meant that when we divided every term by that largest power in the denominator, we ended up with two terms that were going to be equal to numbers and everything else that was headed to 0. If my largest power of x happens to be in the numerator, like in that first example, then when we divide everything by the biggest power in the denominator, not all the x's are going to cancel out. And we're still going to have an x left on top, which means that's going to push us towards positive infinity. In that second example, where my biggest power of x is in the denominator, when we divide by that biggest power of x in the denominator, it means that all of the x's are going to cancel out on top, but we're going to end up with a 0. So we'll end up with a 0 over something. That's why we got our 0 over 3 and we're headed to 0. Now, it's nice to know those rules, but for sure, if you're in Dr. Kuba's class, you don't get to just look at it and say, hey, the biggest power on top and the bottom are the same. I know it's just going to come out to be the coefficients of those terms. For sure, in Dr. Kuba's class, you're going to have to show the work. I'm going to approach this limit problem the same way that we approach the other ones, which is I'm going to think about what happens when I plug in that infinity. Well, in the numerator, when I plug in infinity, I get infinity. And in the denominator, when I plug in infinity, I also get infinity. So the thing that we've been using is to say, well, if I get infinity over infinity, I'm going to divide by the largest power in the denominator. And I know some folks were saying that the square root was throwing you off, and I agree. So I'm just going to divide by the largest power that's inside of that square root. So in the denominator, I'd be thinking about this as x squared over x squared plus 4 over x squared. But secretly, what's the square root of x squared? Yeah, I got an x. It's almost x. We'll come back to that in a second.
The absolute value?
It's totally absolute value of x. So if I take the square root of x squared, this is equal to the absolute value of x. So we can divide by x squared inside of that square root, but in the numerator, because we don't have a square root, we would actually be dividing each term by the absolute value of x. And I know that's weird, but that's how we're going to deal with it when we've got one of those square roots. For those of you that are in Dr. Kuba's class, he loves to put this question on exams. I mean, not exactly this question, but he loves to put a question that has a square root and you're having to find the limit on exams. So I wanted to make sure that we had done one. Now that we're here, now that we can go through all of our simplification stuff, so the limit as x approaches infinity, since we're approaching a positive number, oops, I didn't mean to erase that. Since we're approaching a positive number, a really big positive number, x divided by the absolute value of x is just 1, because I know that x is a positive number, so absolute value isn't doing anything to it. So up here, that's going to simplify as a 3. We still got that 1 over absolute value of x. And then inside of the square root, x squared over x squared is going to be 1. And that 4 over x squared, I can't simplify anymore. And now we're ready to take the limit. So when I take that limit, on the top, I've got 3 minus 0. And on the bottom, we'd have 1 plus 0. And we get 3 for an answer. Now, the fact that the square root of x squared is equal to the absolute value of x, that's what means we have two separate asymptotes when we come back in here to take the limit as x approaches negative infinity. So if I was on the same step but I was looking at the limit as x approaches negative infinity of 3x over absolute value of x minus 1 over absolute value of x all over x squared over x squared plus 4 over x squared. And when we're doing all of that, well, now as x approaches negative infinity, x divided by the absolute value of x isn't going to leave us with a 1. It's actually going to leave us with negative 1. So this part, that x over absolute value of x, that would go to negative 1. I'd still have the 0 and the 1 and the 0. So overall, this thing would be headed to negative 3. Okay, first thing we try with the limit problem is to plug that 2 in. We're going to plug the number in. If I plug the 2 in everywhere, 2 squared, I'm going to end up with 4 minus 2 minus 1, and then in the denominator, 2 minus 2, I get 0. So numerator, I ended up with 4 minus 2 minus 1, so 1. So I got 1 over 0. And I'm going to come in here and I'm going to make that an arrow. Since I've got a 0, I've got a number divided by 0. I know that this is either headed to positive or negative infinity. We just have to figure out which one. So if I think about that plus 1 right there, or sorry, the plus, that says I'm at 2 plus a little bit. If I'm at 2 plus a little bit and then I subtract 2 off, I'm still at 0, but I'm a slightly positive 0, which means we are headed to positive infinity. I don't know what else is going on this graph, but now I know that as x gets close to 2, the y value is shooting up to positive infinity. Whatever else is going on, I know there's some kind of vertical asymptote happening there. And as I approach 2 from the right, I'm headed to positive infinity. What about a horizontal asymptote? If I was going to fill in a little bit more on this graph, if I wanted to find the horizontal asymptote, I'm going to need to know what the limit is as x approaches either positive or negative infinity, right? We're going to have to look at both this time for an asymptote. So if I look towards positive infinity, x squared minus x minus 1 over x minus 2, plug in that infinity, I've got infinity over infinity. My biggest power of x is in the numerator. So one way to think about this is even though they're both approaching infinity, the top is kind of approaching a bigger infinity and the bottom is approaching a smaller infinity, just to give us some intuition that this thing should be getting really big. Now the math that we're going to show for that, I'm going to take the limit as x approaches infinity. I'm going to find the biggest power of x in my denominator and divide every term by that. So I've got x squared over x minus x over x minus 1 over x all over x minus 2 over x. So that x squared over x, that's going to simplify to be an x. X over x is turning into a 1. I've still got that 1 over x. X over x becomes a 1, and then I've got that 2 over x. And finally, if I plug that infinity in at the last minute, I am looking at, well, I've got infinity on top and a 1 on the bottom, which means we're headed to positive infinity. So in terms of an asymptote, that means we have no horizontal asymptote. At least not on the right-hand side of the graph. So whatever else is going on out here, as x gets really big, y gets really big too. Don't quite know what's going on in the middle yet. We need a little more calculus to figure that out. or we need some pre-calc skills. I'm going to be lazy and come back through and switch everything to a negative infinity, but not rewrite it. So if I take instead the limit of x approaches negative infinity, then when I get down to this last step, that's still going to 0, that's still going to 0, but I'm plugging in a negative infinity right there. So that means I've got a negative infinity over 1. So as x approaches negative infinity, my y also approaches negative infinity. I don't know what else is going on in the graph, but that is definitely headed down on that side. And we'll do some calculus in the next few weeks to be able to figure out those missing pieces of what's going on in the middle.